So it's just a matter of you deciding which variation of the difference quotient you like more. I like the f of x, f of a one. We look at our function here, y equals x squared. So that would be my f of x minus f of a, which would be a squared, over x minus a. All right, factor the top and cancel, you're left with x plus a. Limit as x approaches a of that. All right, so our choices are to replace all the x's with a's or all the a's with x's. It really doesn't make a difference because we're going to be substituting in a second. Now, this definition uses c and f of c. That's what most textbooks do, c for constant. It really doesn't matter as long as you're using some constant value. You can go x approaches c instead of x approaches a. That's not a big deal. All right, so I'll go and replace the x's with, the a's with x's. So x plus x would give you 2x. I think this method is slightly, in most cases, aside from those situations where you have to do the factoring by grouping, which is not fun, no matter how I try to spin it, this method almost always ends up giving you an easier time in terms of getting towards your derivative. And since most of the time we need a derivative, we'll call it f prime of x, as a function, it's not the worst idea in the world to get in the habit of replacing your constant with the variable rather than what you would do in the limit unit, which would be replacing the variable with a constant. All right, so that's our derivative. We want it at the point 0.39, and we're only looking for the slope of the tangent. So that's not bad. That's saying to find f prime of 3, replace the x with a 3, and we have 6. So that's telling us the slope of the tangent at 3,9. Turned out that 9 was an extraneous piece of information. If I needed to graph the tangent line, it would not be extraneous. I'd like to have that, although I could figure it out myself. If they just told me that it was at the point where x is equal to 3, I have the relation between x and y. I just plugged a 3 in. If the y that goes along with it, it would be 9 anyway. Right? So in this case, it was a little extraneous. In some cases, it's something that you kind of appreciate when they give it to you, although you can come up with it on your own. The next example, slope of the tangent line to the graph of the cube root function at x equals 0. So this is an interesting one, kind of a precursor to the next part of the lesson. Screwed up?
Question going back. So it's asking to find the slope. So why does the slope change if the equation is 2x?
Why does the slope change
if the equation is y equals 2x, should the slope always be 2?
Well, the equation is y equals 2x, which means depending on where you are in terms of x, your slope will be different, but that's the relation that gives the slope. So if x is equal to -1, you're going to have a different overall slope because 2 times -1 is -2. You're living along a parabola here. And that parabola, depending on where you are on the parabola, is going to have different tangent line slopes. Some pretty extreme in the positive direction, some pretty extreme in the negative direction, and some even equal to 0. But then you might even have some that are just positive, but maybe not very extreme at all, you know? So maybe this is like a slope of, I don't know, 1/2, or this is a slope of 4, right? But depending on where you are, you're gonna end up with a different slope. So this relation tells us what that slope is gonna be no matter where we are along the curve, which is a nice relation to have. All right. Much more challenging to come by if you have a cube root function or any kind of root function. But I still recommend you use the alternate limit definition. Why they call it the alternate limit definition is beyond me. It should be the primary one. It's the better one. I'll still go to a. X approaches a. All right, it's the cube root of x that's my f of x, minus f of a, so the cube root of a, all over x minus a. I remember when I was learning this, I was in I think it was a study group, but somebody told me that you couldn't use this model for this problem because it doesn't work. And I believed them for years until I became a teacher. At which point I looked at it, I was like, first time in years I looked at this problem again, I'm like, wait, what? Of course it works. This method works in all cases, like why wouldn't it work here? So it was a matter of figuring out in what way it would work. The case involving the f of x plus h formula, it's a nightmare for this kind of problem. This one might seem to be nightmarish also. The nightmare is more like you're startled in the middle of the night, not the call the ambulance, I think I'm having a heart attack nightmare. That kind of nightmare. Flop sweat, high fever, heart beating out of your chest. There's a black dog, by the way. I'm terrified of black dogs in my dreams. But in real life, I don't have any problem with them. It's just they're very menacing in my dreams. I have no idea why.
Like in Harry Potter?
Yeah, maybe. It could be the Grimm. Like, it could be along those lines. Maybe that's what caused the problem. I don't know.
The second Harry Potter was the scariest.
It was the third.
The third?
I thought the
What
first
was
one
the
had
snake?
the dog.
Well, the snake.
Whoa, hold on.
Well,
You're killing me here, man. Like,
No, the snake was the second one.
Yeah.
Snake
That one was the
second.
scariest.
okay, I'm just making sure, because
Wait, what was the last
I thought he's talking about Nagini. I was like, you're not even close, man. It's like the second to last one, man.
Nah.
Yeah.
Well, the
The
basilisk.
Dementor.
The basilisk, yeah.
Like frozen basilisk.
Yeah.
Yeah,
That was the scariest.
that was scary. That stuff
That
is
was one of
scary.
my favorites.
That was a good one.
Maybe watch like 20
I
minutes.
remember it.
How old, Mac, how old were you when you saw that?
I read it when I was like in third grade. I guess.
Oh, okay, so
It's still scary.
so you were left to your own visualization of it as a third grader. Yeah, that probably adds to it. I'll allow it. So in this case here, we're looking at a situation where it doesn't really seem like there's much you could do. You might be thinking along the lines of conjugates. Multiply top and bottom of the conjugate to this radical, but it's a cube root radical. I mean, there is a conjugate to it, it's just not pretty. All right, what we can do instead is factor the bottom as if it's a difference of two cubes. Factor as a difference of two cubes. I'll just write of cubes. All right, on the, I think it was the prereq test, that concept came up a couple of times. You were not happy if you lost credit for it a couple of times, but there's a reason, because it keeps coming back over and over again. Maybe I'll just write it on, I'll put it on the whiteboard, I guess. Like the real whiteboard, not this nonsense here. So let me put the rule. Old Algebra 2 rule. You have a cubed minus b cubed is equal to a minus b, a squared plus ab plus b squared. All right, so we would just follow that model, which tells us that whatever we have as our first term in the given binomial, we take the cube root of that. Second term, we take the cube root of that. Then we work off of these guys to come up with the entries in the trinomial. Square this, multiply the two together, square that. And then just make sure you know your sign distribution locked in.
Please excuse this interruption, Dr. Siciliano. I would ask that all work.
So I'm going to take my denominator, x minus a, and follow the same model. So I'm going to take the cube root of the first term and the cube root of the second term. Then I'm going to square the first term here. So that would be the cube root of x squared. I'm going to multiply the two together. So that would be the cube root. Oh, I meant to write the little 3 first. For spacing. XA. And then I'm going to square the last term. My little arrows get messy, but if you follow along, hopefully it makes sense. And if not, I can do it again. All right. The way I remembered the signs, the distribution of signs, I just remembered them, so that's not very helpful. I just remember that this one was always minus plus plus, and the other one was plus minus plus. I don't know. But I read it in a textbook. Actually, no, I didn't read it. A student told me that they saw it in a textbook. I then read the textbook to make sure they weren't making it up. And then I saw what they were talking about, the SOAP method, the SOAP acronym, sorry. Same, opposite, always positive. That acronym always works when you're factoring a difference or sum of cubes. The first sign should be the same as what you started with. The second one should be the opposite, and the last one should always be positive. So if you remember SOAP, that kind of helps out a little bit anyway. Same, opposite, always positive. So now I know what the factored form of my denominator is. And I'll rewrite it just so we have some clean notes. Yeah, it generally looks like it should be making the situation worse, not better, but because we're going to have a nice set of canceled stuff here. And even after the cancellation, it still looks like, well, how's that helpful? It really is. Because I said so. That's the only one we really need, I think, at this point. Yeah. Yeah, the reason why it's helpful is because the part of x minus a that makes it undefined when you substitute an x in for a or an a in for x is this part. When that cancels out, the troublemaker is gone. It's been banished. Poor quality too. So that's our simplified expression, messy handwriting aside. Now I'm going to replace all my, I'm going to apply the limit. I'm going to replace all my a's with x's. If I'm looking for a numerical answer, I can go either way. So basically, if it says find a slope at a particular point, I can replace a with x or x with a. It's just most of the time, they're going to be asking us for functions. So having it in terms of x, at least at some point in your solution, seems to make sense. All right, so on the bottom here, we actually have, it's written two different ways, but we have 3 instances of the cube root of x squared. So if I collect all 3 of those, I end up with this as my derivative, f prime of x. All right, so now, after all that, you say to yourself, well, if I plug in a 0, because I'm looking for the derivative at x equals 0, I get this, which is 1 over 0, which normally would mean no solution or some kind of DNE, but it actually means something more important than that. And it requires at this point us to look at the graph because I haven't taught you about differentiability yet. But what this is going to give us based on the graph, which looks something like this. Here's 0. You're looking at a line that goes vertical. That's known as a vertical tangent. But then it begs the question of, okay, well, if I'm not allowed to use my graphing calculator, how would I know that? Well, one way, and this is not the way I would recommend you do it because I'm going to show you a better way in a few minutes, but one way would actually be to plot some points and sketch out what you think the graph of the cube root of x looks like. Cube root graphs aren't too difficult to come by because the numbers, I mean, you would just choose numbers that are convenient. I would only choose numbers that are perfect cubes to plug in for x. So I'd be looking at 0, 1, 8, 27 and get the corresponding y's. And then I would do some negative counterparts for that also. And it wouldn't take too long for you to figure out that it looks like this, right? But like I said, I'll show you in the next page or so, I'll show you how you can come up with that analytically so you don't even have to come up with a graph, which is pretty cool, I think. Insurability. All right, so that last page is kind of like where regular calc would end in this topic. You know, it would be like, all right, now that we've done that, let's spend many days practicing it. Here, this is how we APify. We take it to the next level. We learn about applications of it and such. They eventually get to applications too, but they take a little longer to get there, which is what you would expect. Function is differentiable at a point C in its domain if and only if the function is continuous at that point and the limit of the derivative of the function as x approaches C is equal to the value of the derivative of the function at C, or basically this. Right? I mean, it's a lot of textbook jargon. That's really just saying that the limit of the function, of the derivative of the function exists at a particular point, right? And it's equal to whatever the evaluated function is at that point. But then you have different variations in what would happen if that were not the case, right? So basically, what we're doing when we're testing for differentiability is we're applying our continuity rules to the derivative function as opposed to the original function, right? So I want to see, does the derivative exist at a particular point, right? So meaning, does it give you a nice number? Okay, if that's true, does the limit from the left and from the right approach that number? Yes, then it's differentiable at that point. We have other variations that would occur if the limit does not exist at that point, or the point exists, the point doesn't exist, but the limit does exist. Or maybe the limits are going to some kind of infinity. What would happen in those cases? Because technically the limit exists kind of sort of at infinity. It's just, what does that mean? What does that mean in terms of what the graph would look like? That's what all this stuff kind of takes us through. All right, so we have the first case, which is the corner. A corner is easy to visually determine because it comes to a sharp point. All right, absolute value function graphs are pretty easy to verify in terms of them being corners. So that's a corner right there because they're actually literally corners. Like if I asked you to draw a sketch of a graph that had a corner, you'd probably come up with something like this. What you might not come up with as another example, I need a pen, I guess. Would be something like this. You know, a nice parabola. And then a line attached to it. All right, that's also a corner. All right, so the moral here, is that it doesn't have to be two linear equations coming together to give you a corner. It could be non-linear also. So here's an example of something that's not a corner. Oh, I just gouged a scrape mark out in the nib is shot, that's why. It sure is. All right, so it bows in. I like, you know this by now. Terrible drawing ability. But I'm trying to show that it bows in. This is not a corner. As you said, it's a cusp. No, you did. I just have super hearing. I got someone in period 7 making a inappropriate sexual joke. Yeah, I was like, dude, see me after class. And then I repeated to him exactly what he said, that he thought he whispered to the person next to him. Yeah. Yeah, I mean, I'm like, I most closely identify, I think, with Daredevil, except for all the physical abilities. Like I can't do ninja stuff, but I'm like legally blind in my left eye. My right eye's not much better, but I can hear everything.
Did the iPad here?
What's that?
Did the iPad here?
That was a joke. Yeah, you didn't get it. Right. No, when you said it, I was like, wait, what's that? You know, like just to, okay. It wasn't a good one. Okay, so it's not really your fault. The iPad did hear. Yeah. So if you go back and watch the videos from Thursday, I believe it was, you'll hear it.
I hate watching them, going back and watching them. I can just hear myself coughing in the background.
That means you're watching that. I mean, as long as it gets a thumbs up at the end and no negative comments, I'm happy camper. A student in my college class put a negative comment up there, and I was like, oh, and by the way, the one of you who put a negative comment up there, thanks a lot. And a student like sheepishly raised his hand and said, wait, I thought you said that if I had something to say, to put it in the comments. It's like, no, I don't want the whole world to see how stupid I am. Can you please, like, or at least maybe they'll see it through the video itself. I don't want it to be, I don't want their direction, I don't want them directed to where my stupidity happened. Like, let them figure that out on their own. Don't point it out to them. Like, don't make it easy for them.
Mr. Can, did you purposely put like that?
Typos? No, I did not.
The meme with the high ground Anakin.
I did.
Yeah.
I did. Yeah.
I was looking at the unit 1. I was like, oh. Okay.
Yeah, that's. I do that for unit tests. Like that's my way of pointing out to people not to try to cheat during a test, because I have the high ground. The consequence is not that I will chop your arms and legs off with a lightsaber, but like academically maybe that would be what would happen, you know, like as a metaphor. But yeah, I did that because this is my 19th year teaching, and during a test I see it all the time. It's just so stupid. I want people to stop. Like the pretend stretch. Oh.
Do people do that?
Yeah, people still do that. like, what are you doing? Especially when I'm standing right behind you, watching you. Yeah, because it only takes within like 10 seconds of the test starting for me to know who the people I have to worry about are. And so I just make my way over to their section of the room. And then I bring all my stuff with me. And we'll start, like if I'm grading papers or doing computer work, I'll just do it on the counter behind them. Or I'll do it over on the table behind, you know, and I'm just watching. But I also, I do this bad boy. Did I told you about this one yet? No? So I pretend that I'm on my phone.
You recording?
Yeah.
That's so scary. Should I play it back for the cheaters?
Yeah. Well, I didn't cheat during a test, really. You sure you didn't?
That would be terrifying.
So, I mean, I started doing that only when I realized that there was nothing stopping you all from like recording me during a class and it going up on YouTube and painting me in an unflattering light. I was like, oh yeah? All right, well, at least I can do is bust a few cheaters in all of this, so if I can, I will.
I'm now picturing you like showing your friends, look at this cheater I caught.
Yeah, look at this cheating bum. Loser. No, it's not that bad, but at a teacher convention, jeez. Yeah, that's one thing I actively try to avoid. Move your reference, anyone? No, okay. So
Wait, what was the reference?
If you
that I
catch someone,
actively, that's one thing I actively try to avoid.
if you catch someone though, just like to do now, just like watch this video.
What's wrong with this picture? Details, man, details. Okay, so anyway, justify a corner, show the function is continuous at C if necessary, meaning if you have a function that's obviously continuous everywhere, then it's not something that you would need to show. Like if you're looking at a parabola, it's common knowledge that it's everywhere continuous, so you would not need to use limits to justify its continuity. But a piecewise function, most certainly. All right, so we'll address continuity first in the 3 steps, and it's also a good idea to do this because what happens is, going into this part of the unit, people understand how to find a derivative, they just forget how to test for continuity. So if this is going to be discontinuous, it would have to happen at the endpoints because each component is linear, and those are continuous just by the nature of life. So I need to first find f of 0. That only applies to the second piece of the function. So I'm not going to write the x. Just plug the 0 in for x, and you get 0. All right, so we know a point exists there. All right, one little bit of information that's very important is that if a function is not continuous at a point, it's never going to be differentiable at that point. Differentiable is just a fun way of saying derivativable. Actually, derivativable is a fun way of saying differentiable. Yeah, I agree with that. So, yeah, it's really, that's what it comes down to. It's the idea that can you find a meaningful derivative at that point? If it doesn't exist there to begin with, then how could you, right? So I know that there's a point there. Now I need to know if the limits are approaching that same location. So the limit as x approaches 0 of negative x, now that would be from the left, is going to have to be the same as the limit as x approaches 0 from the right of the right piece of this piecewise function, which is just x. Both cases we get 0. So these two zeros are equal. Specifically to this 0. They all have to be equal in order for the function to be continuous. Therefore, okay, whatever. Therefore, f of x is continuous everywhere, or everywhere continuous if you want to speak like a textbook. All right.
In the definition of the corner, like the limit of f prime of x equals L1, is that referring to the derivative?
The derivative, which is what we're going to tackle now. All right, so now what I need to do is find the derivative of my function, f prime of x. The good thing about linear functions is that they're really easy to find the derivative of. Obviously, grammar is not one of my strengths, but we know this from typos. All right, so the limit definition is a useful tool, but it's only useful when you're dealing with situations where you can't conceptualize what the derivative is just by looking at the function. Right? What we're dealing with, again, when we're finding a derivative, is the slope of the line tangent to the curve at any point along the curve. Right? Emphasis on the curve. If it's a line, I'm looking for the slope of the line tangent to this line. Well, what would be the line that's tangent to this particular line? That same line, right? Which has a slope of what? Negative. Well, I only want the slope. -1. Because again, what I'm looking for is the slope tangent no matter where I draw my point. So if I draw a point on the left-hand side, and then try to draw a tangent to that point, the best I can do is come up with a line directly on top of the line that was already there. All right? And since all I'm looking for are slopes, I would just register whatever the slope is of that given line. So that actually happens with all kinds of lines. The only one that's a little funky is the case where you have a vertical line. Although the slope of the line tangent to a vertical line is going to be the same as the slope of the vertical line itself, which would be undefined, 1/0. It's just weird to think of it that way. All right, the other piece would then have a slope of what? 1. So what we get from this, just as a time saver, is that if you have a linear function, its derivative is going to be the slope of that line. It's very convenient. You could do it with the f of x minus f of a stuff, just to verify. It's probably worth the 30 seconds it would take to do it, but some other time, I guess. Right? So then what we need to do is see or justify that the left and right hand limits at that point are unequal. All right? Unequal but finite. So what I now want is the limit as x approaches 0 from the left of the left part of my derivative function, -1. I need to show that that's unequal if I'm going to justify a corner to the limit as x approaches 0 from the right of the right piece. -1 is unequal to +1, but they're both finite. Therefore, we're looking at a corner. All right. This is not a very engaging sort of question. I mean, it's math for the sake of math in a lot of ways. But I mean, it's pure math and there is value to it. It's just when you visually determine that it's a corner, it seems like overkill to have to do all this stuff, but this is the proof that that's a corner. So when you're dealing with applied math, you're dealing with getting answers in context. When you're dealing with pure math, you're dealing with always justifying the why and the how. All right, so this is more along the lines of pure math. So depending on your mentality, it may seem like, wow, this is incredible and cool and stuff. Or it might seem like a complete waste of time. That's where you start dividing into different career paths if you haven't already done so. You know, if you like this sort of thing, then, you know, academia might be for you. If you don't, then you're in the applied fields. All right, so stole my own thunder with the cusp, but that's all right. A cusp, a cusp is when the function is continuous at c, so still looking for continuity. But, and in all cases, you should be looking for continuity because none of this stuff happens if the function isn't continuous to begin with. All right, you don't have to worry about differentiability because it wouldn't be differentiable at all to begin with. All right, so we're looking for the limit as x approaches your constant c from the left. I'm sorry, does that say from the right? What does it say on your papers? From the, oh, go left first. All right, well, I'll take it as a typo. Some of you are,
Reed's already on.
yeah.
Reed was like 10 seconds.
Reed,
away.
let's one type this one.
Yeah, but remember, once you max out, so.
How many?
I don't know how to
is that?
describe this.
Already done, sorry.
3, once you hit your 3, you're done, so.
Well, I don't know if you've accepted.
Exactly, so what I say is, you know, just because you see somebody else putting it in doesn't mean you shouldn't put it in yourself, because you never know. All right, so continuity.
Not worth the effort.
Now in this case, you do see that there is a cusp here, and it is obvious from the graph. Analytically, if I was not given the graph, to know that there was a cusp there to begin with, that could be tricky. And we'll talk about how we determine that just from the equation tomorrow, but for now we're just going to get into the concept. So I'm going to assume that it's happening here, because I have the visual. So I'm going to find first f of 0, which is 0, limit as x approaches 0 from the left of x to the 2/3, would have to be equal to the limit as x approaches 0. Why do I have a 1 there? Jeez. Monday morning. From the right of x to the 2/3. Now, this isn't piecewise. This is direct substitution. So it doesn't matter if you plug it in from the left or from the right, you're going to get the same thing, and in both cases, 0. So therefore, it is continuous. So now I just need to test the limit. So what I need to find is, given f of x equals x to the 2/3, I need to find f prime of x. All right, so this is a little bit more of a doozy because you have to figure out the derivative first. Limit as x approaches a of x to the 2/3 minus a to the 2/3 over x minus a. Ooh. All right, so let's pause and ponder.